The citric acid cycle is an important process in harvesting chemical energy for cellular respiration. It begins with the formation of a 6-carbon citrate when a 2-carbon acetyl group, given by an acetyl coenzyme A molecule, reacts with 4-carbon oxaloacetate. The citrate then undergoes 2 oxidative decarboxylations, each releasing a carbon atom in the form of CO2. Finally, a series of reactions occur to convert the resulting 4-carbon compound back to oxaloacetate. The process creates a total of 3 NADH, 1 FADH2, and 1 GTP, each as a result of specific reactions in the cycle. In the mitochondrial matrix, acetyl coenzyme A reacts with oxaloacetate to form an intermediate citryl coenzyme A. Then the hydrolysis of the thioester bond releases citrate. Next, the citrate is isomerized into isocitrate. It first undergoes a dehydration reaction to form an intermediate molecule, cis-aconitate. Cis-aconitate is then rehydrated, forming the desired isocitrate. Here, the first of 2 oxidative decarboxylations occurs. The isocitrate molecule releases 1 CO2 molecule and reduces 1 NAD+ molecule to NADH. The result is a 5-carbon alpha-ketoglutarate molecule. Next, the second oxidative decarboxylation occurs. Alpha-ketoglutarate is decarboxylated and then bound to coenzyme A, forming succinyl coenzyme A. NAD+ is reduced in the process to form NADH. The conversion of succinyl coenzyme A into succinate is an exergonic reaction coupled with the synthesis of GTP from GDP. The cycle now begins its regeneration of oxaloacetate. Succinate undergoes dehydrogenation, creating fumarate and donating 2 hydrogen atoms to FAD to make FADH2. Fumarate is then hydrated to form malate. Finally, malate undergoes dehydrogenation, forming oxaloacetate and reducing NAD+ into NADH. The oxaloacetate combines with another acetyl coenzyme A in the next cycle. The carbons that leave as CO2 are not the same carbons donated by the original acetyl coenzyme A. The terms 1 and 2 will be used to label the respective carbons of acetyl coenzyme A. Consider isocitrate, the reactant for the first oxidative decarboxylation. Here, it is the 4th carbon that is released. In the second decarboxylation, alpha-ketoglutarate releases the 6th carbon. As the second citric acid cycle begins, carbon 1 will take the place of the new 5th carbon, while carbon 2 will be the 6th carbon. Carbon 2 will therefore be released in the second decarboxylation. The carbon 1, however, remains for a 3rd cycle, moving from the 5th carbon position to the 4th carbon to finally be released in the first decarboxylation. Thus, it takes 3 cycles to eliminate carbon 1, but only 2 to eliminate carbon 2. To review, it takes 3 cycles to release both carbons of an incoming acetyl group. During the first cycle, the carbons of the initial acetyl group occupy positions 1 and 2 in citrate. During the first decarboxylation, carbon 4 is released. During the second decarboxylation, carbon 6 is released. This is why the carbons from the incoming acetyl group are still contained in the intermediates of the cycle. As the second cycle starts, these initial carbons will now occupy positions 5 and 6 in citrate. Consequently, the carbon that now occupies position 6 will be released in the second decarboxylation of the second cycle. The remaining initial carbon in position 5 will still be contained in the intermediates of the second cycle. In the third cycle, this carbon will now occupy position 4 in the citrate molecule and will be released in the first decarboxylation of the third cycle. The intermediate molecules in the citric acid cycle often play active roles in anabolic processes outside of the cycle itself. The low concentration of compounds, however, quickly causes a shortage, potentially stopping the citric acid cycle. The cycle compensates for these lost molecules through anaplerotic reactions, regenerating intermediates through alternate metabolic pathways.